Hi, and welcome to the Introduction to Software Engineering. My name is Reed Holmes, and I'm an Associate Professor of Computer Science at the University of British Columbia. I've been researching software engineering for the past 10 years, and in this class, what we're going to do is we're going to look at applying software engineering principles to large-scale software development. Technology plays an incredibly important role in our modern society. Maybe you're trying to apply machine learning to a specialized domain that you're really familiar with, or you're trying to improve personalized medicine, or apply new algorithms for sustainability within our world. Or maybe you're just trying to build an app. Before these ideas can have impact in practice, they need to be implemented. And for many modern technological systems, this means implementing some form of large-scale software system. The reason software engineering is important in this space is that software engineering gives us guidelines to help us plan, design, implement, test, and evolve these software systems over time. No matter how good of an idea we might have, a failed implementation will greatly hinder the impact that idea can have on the real world. What software engineering can do, then, is to help us to reduce the risks of us building the wrong system. Software engineering is an incredibly diverse field. So now we have an idea, we have something we need to build a system for. How do we go about doing it? Well, first we need to capture the requirements. What is it that we actually want to create? Then we need to come up with a design. What's the high-level structure of the system that we're going to end up building? Now that we have our requirements in design, the next thing we need to do is actually build it. This is the process of writing the program that will implement our system. But just writing the system isn't enough. Once the system is written, we need to validate it and check to make sure it's actually correct and does what we expected it to do. Once our system is good enough, we'll deploy it and put it in front of users for them to try. Of course, no system gets deployed just once. We'll have to continually maintain the system and fix the bugs that those users will report to us. And for any successful software system, we're also going to need to improve the system. That is, we'll have to add new features to the system so we'll have new capabilities over time. Finally, it's important to realize that we haven't been building software for all that long, at least relative to the other traditional engineering fields. So active research is always happening. As we build more and more systems, as a field, we learn what works and what doesn't. In this course, we're going to be talking about a lot of different software engineering techniques, but it's really important to realize that not all of these techniques will apply to every single project. As your experience improves, you will begin to realize which techniques, approaches, and processes work best for each different kind of project, and you'll figure out how to apply them appropriately. The first topic we'll cover is software process, including both traditional and more modern agile processes. Every software system, no matter what you're trying to do, will follow some type of a process that will help you get from your initial idea to your final deployed system. The next topic we'll cover is software specification, because if we don't specify the software that we want to build correctly in the first place, we'll never end up building the right thing. So we'll start by looking at the software specification process and how we do requirements elicitation and validation. And finally, we'll take a look at user stories, which are commonly used in practice today. In the testing module, we'll talk about how we can validate that we actually built the system that we previously specified. We'll talk about white box testing, black box testing, assertions, and testability, which is ways to make our system easier to validate. In the fourth module, we'll take a look at high-level design. This is where we'll talk about abstraction, decomposition, encapsulation, and information hiding. We'll also talk about commonly used diagrams for capturing these high-level design issues. Next, we'll talk about API design and design symptoms and design principles that are commonly applied to all software systems. In Module 5, we'll take a look at low-level design, mainly in terms of design patterns. Some of the patterns we'll look at will include the decorator pattern, the state pattern, and MVC, amongst others. Finally, in Module 6, we'll take a look at some software construction topics. We'll look at how static analyses, lint, and check style can be used to reason about the quality of our systems. And we'll also take a look at how code smells can help us to figure out when we can apply specific software refactorings to improve the overall structure of our systems.